Good morning, students. In this chapter, we will study continuous time Fourier transform. In the previous chapter, we studied Fourier series, analysis of periodic signals, and we derived the Fourier series coefficients using the Fourier series analysis equation. And we reconstructed the original signal x of t from the Fourier series coefficients using the Fourier series synthesis equation. In this chapter, we extend the Fourier series to Fourier transform, and we'll see Fourier transform of different signals and Fourier transform of periodic signals, properties of continuous time Fourier transform, and we'll see how we can be able to solve differential equations using Fourier transform. As you know, periodic signals can be represented using linear combination of harmonically related complex exponential signals using Fourier series. However, if we can be able to solve this for non-periodic signals, we call non-periodic signals aperiodic signals. How we can do it? Of course, we can do it by assuming a non-periodic signal is periodic with infinite period. So when the period t becomes infinite, what will happen? Omega naught is, as you know, 2 pi over t, and omega naught approaches 0. That means the spacing between the frequency components becomes smaller and smaller, and in the limit as t goes to infinity, it becomes 0. So the Fourier series will become a continuous function of omega, and that gives us to Fourier transform. And instead of the summation formula, we will have the Fourier integral formula. For example, you see this one. This is a periodic square wave signal, and this is, for example, for period 4 times t1, we have the spacing between the frequency components like this. And as we increase the period t, the spacing between the frequency components becomes smaller and smaller. And in the limit, this becomes a continuous function of omega. And that means we are coming from Fourier series to Fourier transform. So finally, this is how you can follow the derivation of Fourier transform formula. But the final equation is very important here, is how we find the Fourier transform as a function of omega. X j omega as a function of omega is the integration from minus infinity to infinity x of t e to the power of j omega t dt. This is called the analysis equation, and it will be a function of omega, and we can reconstruct the original signal from the Fourier transform by using the synthesis equation. This is equal to 1 over 2 pi from minus infinity to infinity x j omega e raised to j omega t d omega. This is called the synthesis equation. So when we do Fourier transform, we are going from time domain to frequency domain. So when we go from time to frequency, we use the analysis equation. When we go from the frequency domain to time domain, we use the synthesis equation. And please keep in mind the formula, the integration formula will be converging or will be finite for signals having finite energy. That means from minus infinity to infinity, absolute value of xt squared dt less than infinity. Now let's see some examples in the notes I posted in Blackboard. Okay, before that, I just want to let you know, in some books, we find the Fourier transform that's changing from time to frequency as a function of f. So when we do as a function of f, we have the relation between omega and f. Omega is 2 pi f. Then the derivative of omega with respect to f is 2 pi. Okay. So in the analysis part, no problem. This will be a function of omega f, and omega will change to 2 pi f, and we will have this equation, x of f from minus infinity to infinity, x of t times e raised to j2 pi f t dt. In the synthesis part, we replace d omega by df. So how we replace d omega by df? Then we differentiate this with respect to f. D omega by df is 2 pi. That means d omega is 2 pi df. Then 2 pi will cancel 2 pi. And we have this equation. This is a synthesis equation, x of f e raised to j2 pi f t df. But for this book, we use x of j omega. Okay, so that means x of j omega means from minus infinity to infinity, x of t raised to j omega t dt, and the inverse Fourier transform, which is this one. Now let's do some examples. The first example is very simple example. Let's say the signal x of t is Dirac t, which is an impulse. You know, the impulse is equal to infinity at t equal to 0, at t is equal to 0, and 0 otherwise. But the integration of the impulse, as long as we include the impulse, this is zero, integration from 0 plus to 0 minus Dirac t dt is equal to 1. Okay, so let's find the Fourier transform of the impulse. We use the formula from minus infinity to infinity, x of t raised to j omega t dt. Okay, replace Dirac t. Now, Dirac t multiplied by e to the power of j omega t. The second function, this product is 0 except at t equal to 0. So at t is equal to 0, this will be e power of 0. E power of 0 is 1. Then it will become the integration of Dirac t dt, which is equal to 1, which means the Fourier transform of Dirac t is equal to 1. And we are interested in the magnitude and the phase. The magnitude of 1 is 1, of course, and the phase is 0. Okay. In MATLAB, we have for the magnitude, we have the abs function, ABS, and for the phase, we have the angle function. Okay, now let's try to find the Fourier transform of x of t equals to Dirac t minus t naught. T minus t naught means shifted by t naught. Let's say t naught is positive, then shift the impulse to t naught to the right, which is at t naught here. And what is the Fourier transform of this? Again, we apply the formula, x of t e minus j omega t dt. Okay. Now, again, the product of the exponential function and the impulse will be 0 except at t equal to t naught, because the impulse is at t equal to t naught. Therefore, at t equal to t naught, we substitute t to t naught. Then e to the power of j omega t naught will be constant with respect to the integration dt. Therefore, we can take outside of the integration, and we have this. And the integration of the impulse is 1. Therefore, the Fourier transform of Dirac t minus t naught, e to the power of j omega t naught. Okay, if we compare with the previous one, we can check the magnitude. What is the magnitude of this? Because I have j here, the magnitude is 1, and the phase is minus omega t naught. So they are different in phase, but in magnitude they are equal. Now let's see the third example. The third example is exponential function, x of t e to the power of a t ut. A is greater than 0. This is a decaying exponential function. You see, it starts from 0. Why? Because a is greater than 0. Again, let's apply the formula from minus infinity to infinity, x of t e to the power of j omega t dt, e to the power of at. Then we add the exponents. Then we have a plus j omega t dt. Then integrate from 0 to infinity. Why? Because of unit step. Remember, unit step function u of t is equal to 1 for t greater than 0 and 0 otherwise. Therefore, this is the rule of integration for exponential function. negative 1 over a plus j omega from infinity to 0. This will be because this part is e raised to minus infinity, e raised to minus, because a is positive, e raised to minus infinity is 0, 0 minus 1 is minus 1. Then we have 1 over a plus j omega. Again, when we change to polar form this, we have the absolute value of this is 1 over a plus omega square, and the angle is minus tan inverse of omega over a. Most of the time we are interested to plot the absolute value or the absolute value of xj omega and the angle or the phase part. So if we plot this to omega 0, 1 over square root of a square, 1 over a, and it will be when omega goes to positive infinity, it approaches to 0, negative infinity, it approaches to 0. At omega is equal to a, I will have 1 over square root of 2 times a. This is a minus 3 dB point. Remember, when we study the RC circuit, we were talking about the minus 3 dB point. That means the tail log of the maximum at this, the value of the amplitude at A will be tail log absolute value of xj square, and then it will be tail log of the maximum square minus tail log 2. It will be minus 3 dB below the maximum. So this is a minus 3 dB point. Okay, if we plot the phase, the phase is as a function of omega. It is tan inverse of omega over a. This is similar to the RC circuit. When omega goes to infinity, tan inverse of infinity, pi over 2. Because I have a minus here, it will be minus pi over 2. Okay, and at a, tan inverse of 1, pi over 4, and it will be minus pi over 4, and so on. So this is the phase plot. Okay, the other example is the rect function. Rect function is a square pulse signal. Okay, we call this rect function. X of t is a rectangular function. In other words, x of t is equal to rect of t over 2 times t1. 2 times t1 is the width of the pulse. Okay, if you see, for positive, I have from 0 to 1. For negative, from 0 minus t1, then the overall width is 2 times t1. Let's find the Fourier transform of this. Okay, so xj omega, by the way, this can be used, for example, for communication, data communication. For example, when we are sending binary 1, we can send this pulse, and binary 0, 0, binary 1, send this pulse, binary 0, 0, and so on. So xj omega is from minus infinity to infinity x of t e to the power of j omega t dt. And because the pulse is between t1 and minus t1, we integrate from t1 to minus t1, and the amplitude is 1 e to the power of j omega t. So we are integrating with respect to t. From the rule of integration, we have negative 1 over j omega e minus j omega t. From t1 to minus t1, if we evaluate, this is equal to negative 1 over j omega e minus j omega t1 minus e j omega t1 positive. Then if we rearrange this, we get 2 sine omega t1 over omega. This function, it's a function of omega. It looks like the sinc function. You know, in communication, it's we know the sinc function. Sinc function is sinc of theta. It is equal to sinc of pi theta over pi theta. Okay, that means when we change it to frequency domain, the rectangular pulse, it becomes an infinite period sinc function, which is a function of omega. Okay, So if we change it, we can rearrange this and change it to sync. And when we change it to sync, it will become this. Now, what is the value at omega is equal to 0? At omega is equal to 0, it's the DC value, 2 sine 0 over 0. Sine 0 is 0, 0 over 0, it's undefined. So we need to use L'Hopital rule, okay, to find the value at omega 0. Okay, by using L'Hopital rule, we should differentiate the numerator with respect to omega, the denominator with respect to omega, and evaluate at omega 0. The denominator with respect to omega is 1. The numerator, it is cosine omega t1 times t1 by chain rule. Okay, then we have 2t1 cos omega t1 at omega 0, which is equal to 2t1. This is the DC value. Or we can find it from the original equation. How we find? We substitute omega is equal to 0 from the Fourier transform, and it will be the integration from minus t1 to t1 e raised to 0. E raised to 0 is 1 dt from t1 to minus t1 to t1. Okay, so that's all. And in general, actually, at t equal to 0, we can, if we want to get the value of the signal at t equal to 0, we can use the spectrum xj omega. Xj omega is called the frequency spectrum. Then from minus infinity to infinity, this will be e to the power of 0 d omega. So this is the value of the signal at t equal to 0 is given by this. The integration of the spectrum from minus infinity to infinity d omega and divided by 2 pi. As an exercise, you can plot the Fourier transform of e raised to minus 5t, plots the magnitude and the phase. You can use MATLAB. Remember to plot the magnitude, you can use the abs function, and the phase, the angle function. Okay, Fourier transform of periodic signals. Okay. For periodic signals, okay, let's say I have e to the power j omega naught t. What is the Fourier transform? The Fourier transform of this is 2 pi Dirac omega minus omega naught. How comes the Fourier transform of this exponential function becomes this impulse function? We can prove that by going from frequency domain to time domain. Okay, let's find x of t. X of t is 1 over 2 pi from minus infinity to infinity x j omega e raised to j omega t d omega. Now substitute this, the Fourier transform, 2 pi Dirac omega minus omega naught. 2 pi will cancel 2 pi. Now, if we multiply the Dirac omega minus omega naught means an impulse at omega naught multiplied by e raised to j omega t. When we multiply with e raised to j omega t, we have a value at omega naught. At all other places, it is 0. So this omega will change to omega naught. Then it will become e raised to j omega naught t. Then it is no more a function of omega. Then we can take outside the integration. Then it will become e to the power j omega t. The integration of the impulse Dirac omega minus omega naught from minus infinity to infinity d omega. But this value is 1, so this is equal to e raised to j omega naught t. So by going from frequency to time, we proved that the Fourier transform of e raised to j omega naught t is 2 pi Dirac omega minus omega naught. If this is important because if I have periodic signals, we can express them by using Fourier series, by using this formula, as you know, a summation ak e raised to jk omega naught t. Therefore, okay, what is the Fourier transform of any periodic signal? It will be summation 2 pi ak Dirac omega minus k omega naught. Okay, this formula is the Fourier transform of any periodic signal x of t, which is expressed by Fourier series formula this. Okay, let's solve this example. A cos omega naught t. What is a Fourier transform? A cos omega naught t. By using Euler formula, we can change it to this: a over 2 e raised to j omega naught t plus a over 2 e minus j omega naught t. For this one, we have this. Okay, and for a over 2 e minus j omega naught t, we have this, and we have two impulses, one at minus omega naught and omega naught, with area, of course, this amplitude a pi and a pi. This is an impulse. Remember, the impulse, it is not the amplitude, but the area when we integrate. So we have two impulses at minus omega naught and omega naught. Okay, so that's all about the examples, and these are more examples you can read. And this is the same thing what I explained about Fourier transform of periodic signals. If I have cos omega naught t, and I will have pi Dirac omega minus omega naught, pi Dirac omega plus omega naught, two impulses at minus omega naught and omega naught. And if I have a periodic impulse train, this is Dirac t minus nt. What is the Fourier transform? First, we find the AKs. The AK is take one period from minus t over 2 to t over 2 and integrate it. The integration of the impulse is 1, because at t equal to 0, this is e power of 0, and this integration is 1, it means 1 over t. So we found the AKs are 1 over t, and we put it in the formula, in this formula, summation 2 pi ak Dirac omega k minus omega naught. Therefore, we have 2 pi over t Dirac omega k times omega naught. Omega naught is 2 pi over t. And we have, again, in frequency domain, an impulse train, okay, with amplitude here 2 pi over t, 2 pi over t, and it is repeated every omega naught. That means, so I have periodic impulse train in time domain and periodic impulse train also in frequency domain. Okay, I hope you understand these examples. In the next lecture, we will study properties of Fourier transform. Please, again, try to do the examples by yourself to have more understanding. Thank you for listening to this lecture.